Let's look at an example of how we would apply the equilibrium constant Kc. So as we can see here, the concentration of the products, C, is divided by the concentration of the reactants, which will always give a constant value which we call K, C for the concentration. So K is for constant, C is for concentration of solutions, and concentration is always measured in moles per dm cubed. So the square brackets identify that it's in moles per dm cubed. Now to convert that into the units, for this simple example here, we have the concentration of C, moles per dm cubed, divided by concentration of B, moles per dm cubed, divided by the concentration of B in moles per dm cubed. These two cancel out, top and bottom, so we're left with 1 over moles per dm cubed. And what we do here is we simply reverse the sign. So for example, a half would equal 2 to the minus 1. So 1 over 2 to the plus 1 becomes 2 to the minus 1. So here we reverse the sign. So 1 over moles becomes 1 over moles to the minus 1. And dm to the minus 3 becomes dm to the plus 3. We're now going to look at an example of such an equilibrium, and this is when we react nitrogen with hydrogen gas to make ammonia. In this, we haven't got a 1 to 1 to 1 ratio, we've mixed it up. So 1 mole of nitrogen reacts with 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. So now when we write the equilibrium expression, the concentration of ammonia is the product, it's on the top. But now, because the stoichiometric ratio is 2 moles of ammonia, we square the concentration of the ammonia. On the denominator are the reactants, 1 mole of nitrogen, multiplied by the concentration of hydrogen, but we need to cube the concentration of hydrogen because, as we can see here, the stoichiometric ratio is 3 moles of hydrogen, so we cube it. Let's now go to work out the units for Kc because they're going to be different than in our first example. This time, if we look on the top, we have 2 moles of ammonia squared, so we square, so it's moles per dm cubed times moles per dm cubed. On the bottom we have 4 moles altogether, so that's moles per dm cubed for our nitrogen times moles per dm cubed times moles per dm cubed times moles per dm cubed, because we have cubed the concentration of hydrogen. We now start to cancel out, which leaves us with 1 over moles per dm cubed times moles per dm cubed. Moles times moles is moles squared. dm cubed times dm cubed is dm to the minus 6. We add the indices. Let's now bring this to the top, so it becomes moles to the minus 2 times dm to the plus 6. In this question, we've been told that the initial amounts in moles of the carboxylic acid and an alcohol is 0.1 moles. We haven't yet formed this product called an ester. We've got no moles of that and 0 moles of that. So this is from page 115 on Caboodle. We're going to be using what is called the ICE method. This is the initial amounts in moles. This is the change. And this is the equilibrium amounts. So it follows, we are told that we have got at equilibrium 0.033 moles at equilibrium of the ethanoic acid. So if we started with 0.1, the change is 0.1 take away 0.033, which means 0.067 moles have reacted. It therefore follows, because this reaction is in a 1 to 1 to 1 ratio, so we've got 1 mole of this, 1 mole of this, forming 1 mole of the ester and 1 mole of water. It therefore follows we must have actually formed 0.067 moles of the ester, and therefore we've also formed 0.067 moles of the water because they react in a 1-to-1 ratio. It also follows that the change in the amount of alcohol that has gone down, so we started with 0.1, and if we formed 0.033 moles of the carboxylic acid, we also must have formed 0.033 moles of the alcohol. And therefore we have our change is minus 0.33, which is equal to 0.67. So our equilibrium amounts are the same amounts of alcohol and carboxylic acid, and we have also formed 0.067. We had 0 moles, so we had 0 plus 0.67. We had started with 0 moles of water, so we're now adding 0.067 moles at equilibrium. Now we have our equilibrium amounts. What we need to do is convert to concentration, and we know that concentration or molar concentration is number of moles over the volume, and the volume is in decimeters cubed. They've already converted this to decimeters cubed for us. So now we write our equilibrium expression, Kc. And Kc, remember, is the concentration of the products, in this case the ester and water, divided by the concentration of the reactants, and that is the alcohol and the carboxylic acid. So I'm just going to simplify this and say that that is equal to the concentration of the ester times the concentration of the water divided by the concentration of the alcohol multiplied by the concentration of the carboxylic acid. Writing out our equilibrium expression, the concentration of the ester times the concentration of water divided by the concentration of alcohol times the concentration of the acid. So as I said, we're converting this to concentration, molar concentration, moles per dm cubed. That's what these square brackets mean. So we divided the number of moles, the amount, by the volume. Don't dive for your calculators just yet, because what we can now do, seeing as there are equal moles of both on both sides, the volumes actually cancel out. But it's not just the volumes that cancel out. If we to put in the units, so we know the units for Kc for concentration are moles per dm cubed. So on the top we've got moles per dm cubed times moles per dm cubed. We also have on the bottom the concentration of the acid and the alcohol, which are both moles per dm cubed times moles per dm cubed. So as you can see, what happens, they cancel out. So in this instance, Kc has got absolutely no units, and the value comes out to 4.1, no units. Let's now look at an example of a question from a recent paper 2. So this was from paper 2, 2018. In this question it tells us that we've got some carbon monoxide and hydrogen allowed to reach equilibrium in a container. There's the volume in centimetres cubed, and they've given us the temperature because we know that the value of any constant is affected by the temperature. They've given us the equilibrium amounts in moles, and they've given us the volume. So all we need to do now is to write an equation for the reaction, write the expression for Kc to find out the value of the equilibrium constant. So it's pretty straightforward. Earlier on in the question we were given the equation, and what you've got to be very careful of is that you don't forget that usually part of your answer is in the beginning of the question. So this was from the page overleaf. So there's our carbon monoxide, there's our hydrogen, and there is the methanol that's being produced. So again, I'm going to use the ICE method. This really was a simple question because what you'll notice is that we were given the equilibrium amounts. So we can ignore the initial, we don't need to know the change because we've been given the equilibrium amounts. However, we still need to convert this into concentration, molar concentration. So as in the last question, we know that molar concentration is equal to the number of moles the amount in moles divided by the volume in dm cubed. Well, in this case, the volume is in centimetres cubed, so we'll just annotate that and tell ourselves that that is 0.5 decimeters cubed. So we can now write down the molar concentration in moles per decimeter cubed. So each of these equilibrium amounts will need to be converted into concentration. I'm not going to dive for my calculator just yet, so that's 0.340 divided by 0.25 dm cubed, not 0.190 divided by 0.25 dm cubed, not 0.016610 divided by 0.25. Let's now write our equilibrium expression out, Kc, and remember that is equal to the concentration of the products divided by the concentration of the reactants. So in this case, that is equal to the concentration of our methanol, put square brackets round, remember that means moles per decimeter cubed, divided by the concentration of the product, and since there's 1 mole of carbon monoxide, that's simply to the power 1, but don't forget we are reacting 2 moles of hydrogen, so therefore we need to square this. What we can now do is put our values into the equation. So that's the concentration of methanol, which is 0.0610 over 0.25 divided by the concentration of carbon monoxide, which is 0.340 over 0.25 multiplied by the concentration of hydrogen, which is 0.190 over 0.25, but don't forget to square that value. Even though we weren't asked to calculate the units in this question because the units were given to us, let's just go through it. So on the top we have moles per dm cubed divided by moles per dm cubed. However, this is moles squared dm to the minus 6. And remember, when you bring those to the top, that is 1 over moles squared dm to the minus 6 becomes moles minus 2 dm to the plus 6. Now the next part of this question was a little bit trickier. So this next part of the question, 8.4, told us that methanol decomposes on heating. That is the reverse of the reaction used in its manufacture. So on the last part of the question we calculated Kc, which is 0.311 moles to the minus 2 dm6. This is a reverse equation, and it said here state the units for Kc. So let's just write the expression for Kc first of all. So Kc for the reverse reaction is this time the concentration of carbon monoxide times the concentration of hydrogen squared divided by the concentration of methanol. It must follow, therefore, that the value of Kc is going to be 1 over the value that we got for the reverse reaction, which is 1 over 0.311. And since the units for that one were moles to the minus 2, dm to the minus dm to the 6. The value for this is, the units of this are going to be, well, we can actually calculate it two ways. 1 over moles to the minus 2 dm to the 6. So on our calculators, that comes out to 3.22 moles squared dm to the minus 6. Even if you couldn't get that this was just the inverse because it was the reverse equation, so it would be 1 over kc, you still could have worked out the units yourselves, because it's moles per dm cubed times moles per dm cubed squared, so these two cancel out, and that's how you end up with the units. In this reaction, in this question here, which came from paper 1 2017, this time we were given the equilibrium expression and we were given a reaction, but this time they weren't in a whole number ratio. 1 mole of P reacts with 1 mole of Q to give 2 moles of R, and we were given the equilibrium expression. And what we needed to do was to find, in terms of X, the amount of moles of R in equilibrium mixture. So what we're going to do here is apply our ICE rules. So we have been given the amount in moles at equilibrium of both P and Q. They have told us that we are left with 1 minus X moles of P and 1 minus X moles of Q. So what was the change? Well, it's gone down by X moles. It's dropped by X. So the change is minus X moles, and the change therefore in Q must have been minus X moles. And therefore, the amount of R that's formed is plus, but not X, 2X, because the ratio is 1Q to 2R, 1P to 2R, so therefore 2X moles of R were formed in the equilibrium mixture. Next part of the question, for 3 marks, you are asked to now calculate a value in moles per dm cubed for the concentration of R. So what we were to do was to now substitute in our values into the expression for Kc, which had already been given to us. So having substituted in our values, the concentration of R squared divided by the concentration of P times the concentration of Q. We are this time given the value for Kc, which is 3.6. So we're now left with solving this equation to find X. And quite simply, all you need to do is to take the square root of both sides to get rid of those pesky square values. So that comes out now as the square root of 3.6 is equal to 2x over 1 minus x. Once you solve this algebra problem, x comes out to 0.49 moles, but don't stop there because we're asked for the equilibrium concentration. And since the container was 1 dm cubed, and remember that R is 2x, therefore the concentration of R had to be 2 times 0.49 divided by 1 dm cubed, which came out to 0.97 moles per dm cubed.